Hello and welcome to Mathematics with Simon. I'm Simon and this rather dignified and handsome dog is Chewbacca. Today it's Calculus 2, differentiating y equals x squared. So in Calculus 1 we realised that there's two things that calculus allows us to do. It allows us to understand change and the rate at which quantities change. It also allows us to calculate the area and volume of a broad range of shapes and objects. So today we're looking at the first one, change. It doesn't smell at all. You don't smell at all. So let's look at a practical example. Y equals 4x. Say x is the year and y is the amount of money in your bank account in thousands. How much is in there and how quickly is it growing? So in year 1 there's 4,000, in year 2 8, in year 3 12, in year 4 16 and so on. Each year it is increasing by 4,000. So each year it goes up by 4,000. It's pretty easy to understand. Let's look at it as a line. Okay, he's actually going to knock the TV over, the computer over. Okay, it looks like this. If we think about it as y equals mx plus c, m is the gradient, so m is 4, and c is 0. And the point is the gradient is the rate at which it's increasing, and we can see it's going up by 4 every year. But what if it was more complicated? What if y equals x squared? So x is the year and y is the amount of money in your bank, and you've got y equals x squared. So in year 1 it would be 1,000, in year 2 it's 2 squared, which is 4,000, and in year 3 it's 3 squared, which is 9,000. So it's going to look like this, so it sort of starts slowly, then it takes off over time. By year 10 squared is 100, so it's 100,000, so it's a lot of money. So in year 1 it's just 1,000, okay, in year 2 it's 4,000, but by year 10 it's 100,000, so it's a lot of money. And by year 20 it would be 400,000. So we can draw a little table just to say in each year how much is in there and then what's the growth. So in year 5 it's gone up from 16 to 25, so it's gone up by 9. In year 7, it's gone up from 36 to 49, so it's gone up by 13. What we can see actually is the growth is the odd numbers, so it goes 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. If someone would like to write in the comments why that is happening, I'd be fascinated to see your answers and your interpretations. So we can see how much it grows every year, but we can ask the question, which is how fast is it growing at each actual instant? So at each sort of day or minute or second, how fast is it growing then? And the way we think about this is we think about a small increase delta x. So we think about a point x comma y on the curve. Then we think about a small increase delta x. And this takes us from x to x plus delta x. And at the same time, y is increasing. So y is increasing by delta y. So we've got a point here which is x plus delta x on y plus delta y. The gradient will be calculated as delta y divided by delta x. So the gradient is the change in y divided by the change in x, which is delta y over delta x. It's basically how fast y is changing for a unit change in x. Okay, so what is delta y over delta x? Well, firstly, x plus delta x, y plus delta y lies on the curve. So we know that y plus delta y must equal the square of x plus delta x. That much we know. Now, if we expand out this bracket, x plus delta x squared, we get, so it's x plus delta x times x plus delta x. We get x times x, which is x squared. We get x times delta x, which is x delta x, and then another x delta x, which is 2x delta x. Then we get delta x times delta x, which is delta x squared. So y plus delta y equals x squared plus 2x delta x plus delta x squared. Now we're going to take y from both sides of the equation, which will leave the equation still balanced. We're going to take y away on the left, and we're going to take x squared away on the right, but x squared equals y. It's the same thing, so we're basically just taking y from both sides. Y plus delta y minus y is just delta y, so that's really easy. And then on the right hand side we're also cancelling because we've got x squared plus 2x delta x plus delta x squared minus x squared, so the x squareds drop out. and we get delta y, the change in y, equals 2x delta x plus delta x squared. We then divide everything by delta x. So on the left we get delta y over delta x, and on the right 2x delta x divided by delta x is just 2x. Delta x squared divided by delta x is just delta x. Now this is the sort of calculus trick. This is the big exciting moment. We let delta x get smaller and smaller and smaller and smaller, tending to 0, infinitely close to 0. So what we're doing is making this triangle as small as we possibly can to get a precise answer at one instant. And when we do that, it doesn't affect the 2x, but this delta x goes to 0. So now we write it as dy by dx. This is a derivative. We write the derivative of y equals x squared as dy by dx. And the answer is it's just 2x because this delta x has gone to 0. So at any point on the curve y equals x squared, the gradient, the rate of change, is dy by dx, which is 2x. So we can draw it in this nice little table now. We've expanded the table from before. So say in year 3, the exact rate of change at the end of year 3 was £6 per year. That sort of makes sense because in the year before it was 5, in the year after it will be 7, so just at the end of the year it's going to be 6. It's the average of the two. But we can also use this formula to calculate the rate of change at any point. After 2 3/4 years, we just times 2 3/4 by 2, and we all know that the answer to that is 5.5. Wow, I did that in real time. That was exciting. So 2 3/4 times 2 is 5.5. So at that point, that's how you work out the rate of change. So it's a really useful thing, and it's not just useful for this. It's useful for, say, y is distance and x is time, then dy by dx is speed. So if you know the distance as a function of time, you can use calculus, you can use differentiation to work out the speed. I hope you've enjoyed this. Please hit like if you have, and if you want to see more, hit subscribe and hit the notification bell. We're going to do more derivatives in future. We're going to do more and more complicated functions, then I guess we'll move on to integration. I hope you're all well, and we will both see you soon.